Hello and welcome to this 5-minute short. This one is looking at modeling a control valve in ADRIAN, but this is where we have non-choked flow through the control valve. So this could be a situation where your control valve is fully opened, but the pressures in the system are such that you don't get the choke through the control valve. The choke is somewhere else. And we just need to model the pressure drop through that control valve. So if we move and look at our sheet here, and this is part of a series, so there's another 5-minute short which shows you how to do it in the choke condition. This is the non-choke condition. And what we've got here is we've got our control valve failure relief rate calculation sheet, and it's set up exactly the same as the sheet you can see here. It says choke, so you can see how that got set up in the previous video. Exactly the same situation. We've got a CV of 10, but this time the difference is we're just going for a 1-bar differential across the valve. So what I'm trying to mimic here is with 1-bar differential across this valve, what flow rate is that going to give me? And then from that, I can then estimate what the K value is. I can model it, iterate a little bit to see if I can get a good a fit as I want to get it. So we're doing a low pressure drop, non-choked, 1 bar, how much flow goes across it. So these are just filled in, and again, we picked a CV of 10, we picked a diameter, an internal diameter of 1 inch. These are set up again from the table, and we can go down here and you can see we've got a mass flow rate of 177 kilograms an hour. So that's the flow through this control valve with a 1-bar differential carbon dioxide at the given conditions. So I'm going to go to my ADRIAN, and then this is where this second model appears, my control valve K value. So the way we set this up, again, we're using nodes rather than stagnant vessels. We don't want losses in the system, so we just literally want to measure as best we can the pressure drop across that fitting. So we're not telling it's a stagnant vessel, we're not telling it it's got a gentle or abrupt contraction, it's just a pressure. So it's a node. So again, this is the conditions, physical properties for CO2. We define this as an inlet pressure of 20 bar gauge. The pipe work, we're down to 0 length. We don't want pressure loss in the pipe work. And then similarly on the discharge side, we've got 0 pipe work. And then we've got our exit node. And I'm saying this is 19 bar gauge. Again, it's not a stagnant vessel. So that's giving me my 1-bar differential across that fitting. So I have a little fitting, and this is what I'm trying to model, is the K value of that fitting. And you can see here it's got 11.27, which is a great result, but how did we get to that? So if you press the little ellipses, this opens up your K value calculator. And this is maybe something that you haven't used very often, but this is the user-defined process equipment. If I click in here, what I've basically done is taken the information from that Capri sheet and put it into here. So my pipe inner diameter is 1 inch. The flow rate, 0.96, you can see that's a lovely calculated number. So what I've put in there is that my 1777 kilograms an hour is converted to kilograms a second. That's my density of CO2. 1-bar pressure drop, I've got 1. I'll just press add again, but you'll see it then calculates my K value. So let me just get rid of that one. We don't want 2 of those. But that's how we calculate the K value for that particular control valve, just as a flow loss. And again, I can press calculate on here. This time I'm looking at pipe 2, but I can see I've got 20 bar upstream, 19 bar downstream, 1749 kilograms an hour. If I go to my spreadsheet, I've got 1777. That's pretty close. I could give it a little bit of a tweak. Now, these things are all models if you wanted just to get it a little bit closer. But for me, that's close enough. I've now got a model for my control valve as a K value. And then the next video we're going to do is how do we bring all this together into an ADRIAN model, looking at control valves in a choke and non-choke condition. Thank you very much.